That's Zoom.
Okay.
Oh,
We'll
looks like
just have to.
live
Oh,
on
it's on
YouTube.
YouTube. Okay, then we're good. Fantastic. Okay, so welcome back, everybody. And Emil has kindly agreed to coordinate or moderate this evening's session. So over to you, Emil.
Okay. Thanks once again to Samir and Juan for a very lively back and forth during the afternoon session. And now we begin a panel discussion with the two of them and also Douglas Stanford. And since Douglas is the fresh face, let's start with him.
Okay, thanks. Yeah, my comments are not too closely related to the interesting discussion that's been happening so far. But it's just some point I think is kind of interesting. Then we can get back to the real topic at hand. So there's this proposal, Horowitz-Maldacena final state proposal, and there was a lot of renewed interest in it after the MAMPS paradox kind of broke open this field. And the reason is that it allows both types of entanglement. The two types of entanglement that are required for unitary evaporation and for smooth infall. So I think there's maybe an interesting connection between the replica wormhole story and the Horowitz-Maldacena story, and it's not very well developed. I just want to draw kind of a cartoon. I think the replica wormhole story might be sort of like having a random final state, a random Horowitz-Maldacena final state. So here's a cartoon that's supposed to kind of illustrate the connection. So here I drew two copies of the evaporating black hole, one for the ket, one for the bra, and we left open the region where inside the horizon, where the island lives. And the rules with replica wormholes, roughly speaking, are that you can connect that region together with any other copy of that region, however you like, depending on exactly what you're computing. So for example, suppose we're computing the density matrix of the Hawking radiation. Then we have two copies, one for the ket, one for the bra. And the only way we can connect these things together is like this. And after we connect them, we'll find that the red lines, which correspond to the Hawking radiation, get connected together like this. So the density matrix just looks like two lines connected, just one line with two endpoints, which is like the identity matrix. So this is the mixed state of the Hawking radiation that you get in a naive computation. And here it arises from, I climb from an average over final states. So for any particular final state, you would have some particular pure state of the Hawking radiation, but averaging over them, we get the identity matrix. Okay, from that perspective, it sounds like a random final state is similar to information loss. You just get a mixed density matrix. But it's better because once you determine the final state, it behaves similar to the Horowitz-Maldacena proposal. So here's a cartoon that's supposed to illustrate that. Let's imagine that we're going to first determine what the final state of the black hole is, and then we're going to do one more black hole evaporation experiment and see what the state of the radiation looks like. So now we have a whole bunch of copies of this cartoon. The ones on the left over here represent previous copies of the experiment where we evaporate a black hole, start with different states, and we measure the state of the final radiation. And then over here, we have one more copy, which is the actual experiment that we're doing now. And now you can see that there's a lot of ways for these interiors to connect up with each other. And we can have connections. This one here can connect to any of these. And the effect of that is that the final state of the Hawking radiation that we get out here is going to get projected onto the state that corresponds to one of these previous experiments. So basically the previous experiments that we do that determine the final state end up themselves becoming the projection, themselves becoming the Horowitz-Maldacena projection inside the black hole. So just one comment I wanted to make is that with Rafael Busa, we found sort of a problem with the final state proposal. And Ahmed Almhiri seems to have solved it. I just wanted to advertise his talk at Kyoto. You can find it online. Okay, so that's the only comment I wanted to make. While I was watching the session this morning, I think maybe I just wanted to clarify something. Maybe it was confusing in the paper that we discussed these inner products. And Samir was talking about the difference between inner products and amplitudes. And what we were computing was really inner products, not transition amplitudes. So there were inner products of these states psi I, which were defined as some Euclidean evolution acting on some reference unnormalizable states. And then we were just computing inner products of these states psi I. Okay, that's it for me. Let me stop my screen sharing. Thank you.
Sorry. Yeah, so let's see. Let's have all the panelists present their summaries, and then maybe we'll open the floor to discussions after that, just to keep things moving. So I believe, Juan, you're next. And Juan, you're muted.
Yeah.
Sorry. Now, does it work now?
Yeah, we can hear you now.
Yeah, so I wanted to make a small comment about this issue of non-locality again. So suppose you have a black hole, right? So you have some localized black hole somewhere that has been evaporating for a long time, right? So you have the Hawking radiation that has come out. And then I guess we then imagine throwing something in, right? And we are claiming that through this page curve discussion and so on, that this something in could go into what now will form the interior of the black hole, which will be in the entanglement wedge of the radiation, right? So we have this Penrose diagram where at late times we have the radiation entanglement wedge, right? That extends to the black hole interior, right? And we're trying to understand how some information that is in this black hole interior can be extracted from some computation in the radiation, right? Okay, I think a toy model for this is not the actual situation, but the toy model is, again, this situation with the entangled black hole. So we can think of the, let's say, right-hand side as the original black hole. So this was so the right is the original black hole. The left is the radiation, right? And then if we, so this is the left is the radiation. So if we throw something in from here from the left, right? So we'll, it will be somewhere here. And then if we, by considering the left side plus a little bit of the right side, so we can include some of the degrees of freedom of the right side, so it could be just some small portion, then we can make the entanglement wedge move a little bit, right? And then this mode will be outside of the reach of the right side and can be reached from the from the left together with the small number of degrees of freedom here. And in this case, we can give a completely clear picture of what happens. So that's the standard teleportation story where we get the degree of freedom outside. So we have this nice picture for this situation where we see we can recover some information from the black hole or from the entanglement wedge that was in a region that originally was behind the black hole horizon by doing simple operations that have a clear space-time meaning. Now, the question is whether we can do the same thing for this case where we have the entanglement wedge in the black hole interior. And I think there are some arguments, especially these arguments using the that involve the Python slange that suggest that that should be very complex and a very complex operation. So it's kind of not surprising that we haven't given a simple unitary description of what happens when you recover the black hole information, or what's the real-time picture of what happens, because giving a real-time picture involves giving the various steps that that are necessary for doing, giving a unitary operation. So that's what we can do in real time for extracting the black hole information. So the closest you can do is for some very special states. For this particular case of the thermofield double, you can see something similar, and there is a nice picture. Okay, thank you.
Okay, and last but not least, Samir.
Shall I try to share my screen again?
Sure.
Okay, so let me first just make a couple of remarks in response to the nice comments of Douglas and Juan. So indeed, I apologize, I was calling Douglas's inner products as amplitudes, but they look like amplitudes to me because they were not the normal inner products. And as somebody had pointed out in my actual talk, you can call them modified inner products. So let's do that. They are modified inner products. But the point I was trying to make was that when I go and look at what the modified inner products are doing, they're actually not unitary. And I think people haven't worried about that. And clearly they had to be non-unitary because they are somehow bringing a page curve down while keeping a smooth horizon and not allowing non-locality like in the Marov-Maxwell papers. And that's just not possible by those small corrections theorem. So where does this non-unitarity come in? And the point is, it might seem that once you have the interior of the black hole, I can break this line segment, it's a 1 + 1D theory, it's a line theory line, I can break it, I can join them in any ways. Why don't I have fun with that? But every possible thing you write down in terms of a path integral, unless you allow all the possible states that you can make in between, there are only some things which are actually reflection positive, Euclidean evolutions, which actually have a unitary evolution. So you have to be careful that you haven't actually taken a dot product that leads to non-unitarity. And I found, for example, in the Marov-Maxwell papers and so on, that it is actually a non-unitary dot product. I had presented a dot product here, that a toy version of it. So I would like to talk to the people who do this more offline. Maybe it's not a discussion we can get it now. I just want to mention that that was one of my issues. And indeed, they're not amplitude, but modified dot products, but it's the modification that I am complaining about. So then I had this comment again, maybe it's more like a question then, which I had raised during my talk. And I'd just like to raise the question again so that, let me just go to full screen, so that people could maybe try to answer that. Because I'm still confused about what is the answer that people doing wormholes would like to claim. So here's the experiment. We actually go to CERN, we collide PP bar, make a black hole of mass 100 Planck mass, let it radiate, pass them through a Stern-Gerlach, and see whether it says pure or entangled. I am not sure what answer I have actually heard for this, because I'm still confused about sometimes people using the semi-classical, but then you say it's not the exact theory, and the exact theory, but then you say we can't actually observe that. But this is what the experiment is, right? So this is all we can observe. And so I would like maybe both Douglas and Juan at some point to tell me, do they expect a page curve to be coming down in this, like a pure like a piece of coal or not? And if it is like a piece of coal, then I would claim you cannot have the smooth horizon semi-classical approximation, or you have non-locality. So, but the non-locality, again, to make a comment on that, I also got confused by Juan's comment on what kind of non-locality we need. When I say that we need non-locality to get the unitarity to come out and the page curve to come down, that is actual Hamiltonian non-locality. You need a Hamiltonian interaction between this baby universe and the radiation zone. So if things are just entangled, but there is no Hamiltonian between them, you cannot remove the entanglement. So I think I'm getting a little confused about extracting information and removing entanglement, because they're not exactly the same thing. I could know about something behind something, but I could still be entangled with it. An electron in my room and the other room, they could be entangled, but I may perfectly know what state it is in, so I know everything about the electron. So I'm not trying to get information. Let's just talk about entanglement for the moment. And the claim I make based on this experiment is that either the Stern-Gerlach will tell you the page curve hasn't come down, or if you make it come down, then you can't get a semi-classical approximation to the horizon. If you still also demand a semi-classical approximation, then you must have Hamiltonian non-locality. There must be a non-local term in the Hamiltonian connecting the inside to the outside. So I'm claiming that's the output of the small correction theorem, and maybe clarifying what people say in response to this experiment will go a long way to helping me understand what's being said, because now the exact and the approximate theories are all washed out. Everything is like right here. So let me just stop here and take people's responses on this and other things.
Maybe first want to ask if any of the panelists want to respond to any of the other panelists.
I think if Ahmed is here, I think he could explain the swap test to determine whether the state is pure or not. Or I can do that if he's not here. Okay.
I literally just came back from the restroom, but please go ahead, Juan.
Okay. Yeah. So one way to test whether the state is pure or not is the so-called swap test, where you start with two copies of the state. So you produce the black hole twice, right? In principle, you could get different states from this, and then you're wondering whether different instances of the black hole produce different states, different quantum states. So you produce the black hole once, you get some state for Hawking radiation. You produce it twice, you get another state. And the swap test involves some other qubit, and then you act with some Hadamars and so on. And there is some step where you switch these two states, and then you again act with some Hadamar and you measure this qubit. And if these two states are identical, then you measure when you project this qubit, you always measure the qubit to be up. Okay, so that's a relatively simple operation. And in gravity, it will involve. So we have some evaporating black hole, and so we have two copies of the evaporating black hole. So this is the first state. Let me call it psi. Then we form it again, and we have a second copy of the state. Okay. And then we are collecting the radiation here in the far future. Okay, similar the radiation here. And here we do this control exchange. So we exchange this radiation. And when we do this projection measurements, we have to decide how we are going to join the interiors. Okay. And the idea is that we have the freedom of joining these interiors in different ways. But if we join if we also exchange the interiors, then the idea is that this baby universe should not be associated to one particular instance of the experiment. They are somehow live in some Hilbert space of baby universes, and when we exchange these two states, we could at the same time exchange the two baby universes, and then we will get the result that the state is pure. Okay. So that's how you would see from the point of view of these various wormhole discussions and so on, that the state of radiation is pure. So this is a calculation that tells you the state of radiation is pure. Of course, if you do the experiment, you can just do the experiment on the outgoing pieces of radiation, and that would you would find that the state is pure. You don't need to do any measurement in the interior. This technique of using the interior is just some calculation and technique to evaluate to do this theoretical calculation of what you expect to get if you did an exact experiment. That's it.
So could I make a couple of comments on this, because this is something which I've been trying to understand by reading all these papers. So 2 comments. First, when you actually swap the interiors, that's the kind of new dot product. Like you have many copies. I imagine one black hole I make here, one a kilometer away, one a kilometer away. And then I agree that what goes inside the baby universe, you can have a model where you swap them arbitrarily and so on. But you have to be careful that whatever operation you are giving to the path integral, when you slice it in a Hamiltonian language, you can have multiple baby universes, number of babies can increase, decrease, all that is allowed, right? Of course. But you have to still make sure that the dot product is actually, the evolution is actually unitary. But in the actual fund of the way of joining that I found in the Maxwell papers, for example, it's actually not unitary. So I'm just saying that I would like to sit down maybe offline people to see how exactly they do the joining in the inside, and let's check that it is actually unitary or not unitary. But the other issue I also had was, what are you saying to the answer? If the way I was doing it in my slide, it was just a Stern-Gerlach, and of course I'm going to do it many times. So it's like your thing, you're doing it many times. And the Stern-Gerlach is showing the page curve comes down. Now with that, do you still want that the semi-classical approximation should be possible at the horizon, in the sense that some combination of the actual complicated quantum gravity degrees of freedom should behave like semi-classical quanta? Is that still a requirement? If you do that, then I will push you into a corner with that, right? Because if the Stern-Gerlach brings it down and you also want semi-classical, then I will really need a Hamiltonian non-locality. So I'm just trying
to see that the Stern-Gerlach brings it down, you need to go beyond the semi-classical description.
So that's what I'm confused about.
It's a complex operation. It's a very complex operation. Well, I mean, it's a precision measurement, and you could see it. Well, if you do the swap test, I can tell you what the answer is. With the Stern-Gerlach, I'm not sure. Really, you would need to do an exponentially large number of Stern-Gerlach. But anyway, with the swap test, you can see it from the semi-classical description, and you can see that the state is pure. You only check that the state is pure, but you don't check what state it is, because getting what state it is seems to go beyond what we know how to do. So getting the actual state, and your Stern-Gerlach discussion would get to the actual state. And that's not something we know how to do. Perhaps you could find the state sort of experimentally by doing the experiment many times, and then you would do what Douglas just said. So you would have had all previous experiments that give all these baby universes where that contain the interior of black holes, and you would join the final interior with the original ones.
So let me just push it a little bit more, just to clarify for myself. So that's why I took the black hole to be just 100 Planck passes, because since 100 is bigger than 1, some black hole physics to some approximation already has started by that time, right? Mm-hmm. So I would say 10 to the 4 is not a very big number. So okay, let's not say it's too bad. If you really make a marketable quantum computer, it will have 10 to the 4 qubits anyway, right?
Right.
So, and then we are going to check its states for the quantum computer, which is marketable, right? So let's assume that we can actually do this.
Yeah, but the number of states is e to the 10 to the 4, right? Or 2 to the 10 to the 4. So you would have to repeat the experiment this many times if you do what you said. But.
No, I agree with that. That's absolutely true. I'm just trying to see why that is important, because to me it looked like, okay, I have e to the 10 to the 4 states, and that's a big number, and it takes me a lot of effort to do that. But somehow that doesn't look to me like a real conceptual issue, right? Because conceptually, even a solar mass black hole never evaporates from the edge of the universe. But let's not worry about that if you don't have to. So just because it is complicated doesn't mean I can't do it, right? But all I was saying was, somebody could object. is that some subtle quantum gravity effects will modify the answer so that the semi-classical answer is different from the quantum gravity answer. But that's what I was arguing about. I don't see that, because the Stern Gerlach in the lab, it has all the quantum gravity acting on it, just like the qubits in the real marketable quantum computer has quantum gravity acting on it. But we don't actually ever use that in our calculations. The lab still works out fine. And I'm sure the quantum computers that we market with 10 to the 4 qubits have quantum gravity acting on it, but we'll never actually use them in the design process. So in some sense, there is not two very different things, which is the quantum gravity corrected answer and the semi-classical answer. So to make them into one thing, I've said, this is the experiment, and whatever it does, it does. So it has the quantum gravity in it. And then the question was, what this experiment sees done e to the 10 to the 4 times, I'm willing to allow you that whatever happened in the interior of the baby universe can all swap. But my claim is, if whatever the baby universe is swap, if I keep that interior evolution unitary and don't allow that to leak non-locally to the flat space outside, I actually can't get the semi-classical approximation of the horizon. So that's what I'm trying to argue. I'm trying to remove the semi-classical stuff and get down to something just in principle measurable. But as you said, very difficult to measure 10 e to the 10 to the 4 times after this.
I have one comment. Samir, you had asked earlier about whether the inner product is positive. And I'm not sure why you're referring to it as a modified inner product. It's the inner product of these states as computed in gravity. And in general, I don't know how to prove that it's positive, but in the model that we analyzed in the paper that you mentioned, in the PSSY paper, there it is positive. And what the inner product of these states is precisely is just, you start with random states. And then you apply e to the minus some coefficient times the Hamiltonian to those random states. And the result, those are the states psi I, is the result of e to the minus some parameter times the Hamiltonian times a random state. And that collection of states as a positive inner product.
So let me say something about it, which may not exactly address what you're asking, because once you come to the random or ensemble average theories, I know very little, and I was just assuming I don't want to be in one such theory. But the problem comes from the following thing. There is something just ordinary quantum mechanics in the lab, which looks very tempting, but is actually not unitary. Suppose I take a box of gas and I say I have some process where I take the atoms one by one and put them into a BEC, a Bose-Einstein condensate. Okay? So there they all end up in one state. Okay, so the model will be like when you break the interior into many segments, then you say they're identical, so I can join any to any. So that's why I'm trying to say you have identical segments, and the dot product modification, which I saw in the Marov-Maxfield papers, just uses the fact that all the different pieces are identical, so you should symmetrize the inner product. If you do that, you actually get non-unitarity. You can't take all the atoms of a gas and have a unitary Hamiltonian, which puts them all into a BEC state, where it becomes n excitations of a BEC, because there's only one state there. You can't lower the entropy that way, as you very well know. There has to be some other state, so the total Hamiltonian is acting on a phase space of the same dimension. So if you cool something down to a BEC, you have to generate heat elsewhere. It's the elsewhere part, if you actually look at the dot product used, for example, by Marov-Maxfield, and I keep going back to that because I don't want to have the randomness anywhere, you will find it's not unitary. Okay. Some states are going to zero norm.
I think you might have the randomness even there. Like just one comment about this randomness, I guess, and maybe about the replica wormholes more generally. So nobody is claiming that this is the final story for the quantum description of a black hole, and people have different perspectives on that. I think that, well, I don't want to put words in Juan's mouth, but my impression of his perspective is that, like, there's some questions that this formalism doesn't answer, so we just shouldn't try to ask them in this formalism. I have a slightly different perspective, which is that if you do ask these questions in this formalism, you get the result of an ensemble average. But that's not the final, that's not the end of the story. For a theory like n equals 4 super Yang-Mills, there will be additional things that have to be included in the computation. and they won't change the answers for simple experiments like the swap test experiment, but they will change the answers for very special things, like if you want to know exactly what the state is. So we have a simple theory that describes an ensemble average, and that simple theory is good enough to answer simple self-averaging questions. And to answer detailed questions like the ones that you want to ask, we need to include more in the bulk theory.
So I
All right.
understand.
You want to respond quickly, Samir, and then I think I see some hands starting to be raised. We may move to opening up to a wider discussion. So, but Samir, if you have a quick response.
Yeah, so I think I just wanted to say this, and maybe we should continue the discussion, offline after the conference. I have really struggled hard over the last year to see what is the calculation which shows me that in the actual true theory, the page curve will come down, while using this effective theory 2D theory to get that conclusion. And I have not been able to understand. So I'm just showing you my inability. I have clearly tried to work through the papers. That's all I was showing you throughout my talk. But I don't see the page curve coming down. Every time I try to follow the paper, what I find instead is either there was a hidden non-unitarity and came down because it's non-unitary, or something else happened. And so I would be happy to sit down with people to see how it came down. The only thing I could see is that you are putting in what you get out. The QS principle looked like just saying that I postulate I cannot put area more than entropy more than area in somewhere, and then of course the page curve will come down. Now,
no, but that's not the way the calculation.
That's all I could get out.
That assumption is not being baked into the calculation. So the way the calculation works is you just try to compute the entropy, and then you follow your nose and follow the rules of gravity, and you find.
I'd be happy to sit over that with you in detail, because I tried to follow the rules of gravity exactly the way you're saying, and I run into all these other difficulties. I run into lack of unitarity or non-locality.
Well, maybe we should talk about one example. Like this model with the brains is very simple, and it doesn't have this lack of unitarity. I'm not sure if by lack of unitarity you mean a non-positive inner product or what, but it has a positive inner product, and the entropy saturates at the black hole value.
So good. We can maybe talk. Obviously, we can't settle that here, but let's talk about that.
We could try. I mean, we could try to settle that here.
Okay.
Well,
that paper, I didn't see it come down. Okay, so I saw that the dot plot you introduced to make it come down is not unitary.
Tell you what, we can leave YouTube running after the panel discussion, and you guys can duke it out. But Nick's had his hand raised for quite a while now, and so Nick, please ask your question or make your comment.
It's really Juan, but also to some extent Douglas. It's this issue of. It turned up in the thread that Kostas Skenderis was asking, and I was asking. In the old Hawking calculation, we know that there's sort of entanglement. Well, we know there's entanglement between Hawking radiation and quanta on some space-like surface inside the black hole, and we've known that for eons. But you seem to be wanting something more to get the information out. So Kostas was asking, and I was asking about how is it that you can get the information or the stuff out of the black hole, and the answer comes in this very, very complicated sort of multiple exotic measurement sort of answer. And I'm trying to get my hand on what that means. Are you actually postulating just simple entanglement between stuff on the island and stuff on at infinity, or are you postulating, as Samir would say, a non-local Hamiltonian interaction by which you can influence and change states inside and outside the black hole? So, clear question, are you wanting non-locality in the Hamiltonian in order to do these complicated measurements?
I don't think we want any more non-locality than that which is present in gravity, which is the fact that space-times can reconnect, and so I mean.
Okay, so that's kind of a weasel word, because you're saying I can put a wormhole in. That's a Hamiltonian operation, if ever I saw. Well, maybe it's not, but it's certainly some modification of the or introduction of some operator in the theory. So it is, I think...
You have to include those things, I think.
So the wormhole creation operator is what I would call the non-local interaction. So you really are asking for something more than just entanglement. You're asking for some kind of Hamiltonian interaction between those states.
Yeah, I think so.
Okay, that's
yeah.
And what then ensures that any cherished principles of local physics are not violated? Like energy conservation or?
Well, energy conservation, I think personally is when you have these reconnections, you integrate over space-time, the point where it reconnects. This can ensure energy conservation.
Does this violate energy conditions as well, or does it? Okay, if you.
Well, I don't know of a proof that it is unitary, but I don't see why it has to be non-unitary.
But it's definitely a non-local Hamiltonian interaction. I think that's clarified something for me very usefully, rather than just being, the thing is that, entanglement's intrinsically linear. It's just taking linear combinations of states. You're doing something else. You're hitting it with an operator that's somehow disturbing the system. And
it also sounds a little bizarre to me. You're adding something to the Hamiltonian, which is connecting, some local I mean, what's the wormhole effectively? It's some bilocal operator that simultaneously twiddles something in the black hole interior and twiddles something far away. So, usually if I have some bilocal operator like that, I mean, it's engineering some energy transfer or similar such, well, it's certainly transferring information. So it sounds a little bizarre to say I'm transferring information at zero cost in energy through such a non-local or bilocal term in the effective theory.
I think you only need the interiors to reconnect. The radiation could live in a place that is perfectly free of any strange interactions. So it's the kind of reconnection you expect in gravity, right? Gravity can have topology change, and we need some kind of topology.
So the topology change for you is confined to the region interior to the horizon?
Well, the region that is gravitational in principle. So if you have,
does that include the Hawking radiation or not? That's the
well, if the Hawking radiation is in a region where there is where the Planck constant is effectively can be taken to be zero, or the Newton constant can be effectively taken to be zero, then no, there will be no reconnections in that region. The reconnections happen in the black hole spacetime.
Which is, in Samir's term, he cut it at R is 100M, R is 4M, and then the horizon. So when you say,
well, I mean, for most practical calculations, let's say inside the horizon.
So you only need connections inside the horizon.
Well, or they might be outside, but you need reconnections in the gravitational regions.
But again, I mean, it begins to sound a little bit like you're saying that there's physics there's non-effective field theory physics going on in the region up to the horizon scale, or not.
Well, I think it's what we expect from a theory of gravity, right? So in a theory of gravity, there are non-perturbative effects non-perturbative effects which allow the spacetime to reconnect. So you have to pay a price, which is e to the minus s for this reconnection.
I guess I'm trying to pin you down on the extent of that reconnection, the extent of those wormhole connections.
Well, I think it's the extent you expect. The extent you expect in a normal theory of gravity. There are effects of order e to the minus s. So in the calculation, for example, of Renyi entropies, you are calculating some observable that is becoming very, very tiny in the original saddle, in the Hawking saddle. And then these reconnections make it bigger.
But Juan, do we need to revisit QED in view of quantum gravity?
Yes, if you want to get the precision of order e to the minus s, yes. But normally we don't care about this precision.
So I see Bogdan Ganchev has had his hand up for quite a while. So Bogdan, if you want to unmute yourself and chime in.
Yes, thank you, Emil. I had a question to Juan, which maybe is connected to this discussion as well, which was for a clarification for, I think he was talking about the non-locality and trying to extract the information about a qubit that was thrown in the black hole after it had evaporated for some time. And then you drew that thermophile double-like picture. And you, while explaining it, you had a comment that this is not much different than teleportation. I wanted to know, did you mean quantum teleportation? And
yes.
Because as far as I remember, quantum teleportation involves also a classic communication between the two parties doing the teleportation. So where does that come in, if that's what you mean?
That was coming in when I was saying that you have access to the left side and also some portion of the qubits on the right side.
But the two sides are space-like connected, aren't they?
Well, yeah. So in the picture, they are in this part of the diagram. They are separated by a space-like region, but we are imagining that that this describes only a portion of the space-time geometry. But actually, they are in some sense close by that you can act on both of them in the full space-time. So you imagine that the left side lives in a quantum computer, and then the right side is the black hole and its environment, and the quantum computer is near the black hole. So you can receive some extra qubits, some extra Hawking radiation that comes out of the quantum computer. Either you can have a machine that measures the Hawking radiation and sends the information, and then that would be exactly teleportation, or I can get the qubits, and then it's not quite teleportation. It wasn't important that it was exactly like teleportation for what I was saying.
Okay. I think Steve Giddings is next.
Monica may have had her hand raised first.
Okay. All right, let's go to Monica then.
I have a disconnected question, just if that's okay, which is just continuing my question during Juan's talk. Do you expect to have islands in evaporating small ADS black holes? And if yes, I mean, what's supposed to mean for the page curve and so on? Do you expect islands / a page curve in evaporating ADS black holes?
So if you have a small evaporating black hole, and so this notion of island depends on which degrees of freedom you are considering. So I assume but what you mean is that I have access to the whole ADS boundary, and in that case, no, I don't expect any island. So you can have the black hole.
Yes, but I'm trying to maybe get some sort of contradiction, because yeah, you don't expect any island, but in principle, I could do some gravitational calculation that's set up similarly to what you presented in your talk. I mean, I can set up some cutoff surface in ADS and try to do very similar calculation to what you're presenting. And what would be the reason to not obtain any island in that case?
Well, here you don't obtain any island because when you consider the whole ADS boundary, you include both the radiation and the black hole. So include both systems, and then you always have a pure state for everything, and it includes the whole space-time region. Now,
but then now suppose that I put my finger at some cutoff, as you are doing.
Yeah. So if this black hole can evaporate into another system, right? So if, let's say, you have ADS and then you couple that ADS to something else, it might be that this radiation that comes out of the small black hole gets into the something else system, and if enough of it gets there, then you could have an island when you consider, you could have an island in that case. So then the interior could be represented by the other system, not the original ADS. It would be the same as what I was discussing in the talk.
Right, but then do I need to make the ADS boundary transparent, or it's sufficient for me to sit sufficiently inside the ADS with my cutoff surface?
Well, I think if you put in your cutoff surface inside ADS, then you would treat you are dividing ADS into two regions, and then once you are dividing it into those two regions, then once you define that, then you could have an island when you consider only one of the subregions.
Right, I see. So there should be some sort of a distance from the boundary at which I start having some sort of island solutions. So,
Yes. The precise mathematical definition of what it means to put the cutoff at some finite location, we don't know it. So we don't know the definition from the point of view of the original ADS theory. But
right, but it's the same that would appear in the flat space calculation.
Yeah, it's the same. Yeah, it's
So-
the same difficulty that you have in the flat space calculation.
So maybe one can get some light on what it means.
Right.
Okay,
Okay.
thanks.
All right, Steve, you're next.
Hi, everyone. I've been enjoying the interesting discussion. Thanks. Maybe just to address the dialogue between Nick and Juan and Emil, just a little micro review of something from the 80s. So regarding this question of wormholes and non-local communication of information and energy conservation, of course, there is this old story where in an approximation, wormholes can be thought of in terms of bilocal interactions. In the end, you can incorporate energy conservation into that story. That's part of that story. And also in the end, you find that you don't actually meaningfully transmit information between the two wormhole lands. There's this whole story involving the alpha eigenstates, the super selection sectors, and so on. Now, I guess one of the interesting questions now is, all of that is in an approximation, and to what extent are we going beyond that approximation in the current story as applied to black holes? And, so that's one thing to think about, but just a little reminder that at least parts of that story have, of course, been spelled out and are understood in that approximation.
But the main thing that made my ears perk up was the statement that in that approximation, there's no information transferred through the wormhole. Is that correct?
Yeah, this was, goes back to this old discussion involving Hawking and so on. But yeah, it sort of looks like you can describe, well, effectively loss of coherence or transfer of information through the wormhole effects. But really what's going on is when you take into account the wormholes and, think about, states that you can actually measure and think about, performing successive measurements that will sort of collapse you into one of these super selection sectors. If you think about it in those terms, then in the end, you end up with a system where you don't have any effective transfer of information. Remember, in the end, that old story led to the fact that we could have an ensemble for coupling constants, basically, which you can think of as non-local correlations. If I change the coupling constant, I do it everywhere. So in some sense, I'm doing something non-local. But in the end, once you're in a state with a definite coupling constant, once you collapse into one of these super selection sectors, then there's no meaningful transfer of information that takes place. So there was that sort of old story, which I'm maybe not giving a very complete accounting of, but I'm hitting on some of the highlights of.
I vaguely remember that collapse on the super selection sectors had to do with integrating over the modular ion positions and so forth of the wormholes. Was it effective integrating out or something like that?
It's true that, yeah, at least the description, say in the Hamiltonian, you could have these wormholes occurring in the wormhole mouths corresponded to operators that could occur anywhere, anytime. So there's an integral there for both of the mouths. And, that would apply, I think, as well in the present case. It's just that, maybe that operator, so to speak, only turns on in the center of a black hole or something like that. It's sensitive to the state because it's an operator. So that at least could be incorporated into the present story. And it's that integral that is one way of thinking about how energy momentum conservation is enforced, and is part of the story about why, in the end, these effects only effectively shift coupling constants to the operators that correspond to the wormhole mouths.
Yeah, I guess I was, with question to one to more broadly, is I was trying to pin down if this new replica wormhole story, it's telling me something about information getting from inside the black hole to outside the black hole. And it's not just entanglement, it can't be, because that's a simple linear superposition of states. It's got to be something more. And I guess I'm trying to pin down what that something more is. And I think Juan said it, but I'm still trying to get my head around it. There is some bilocal operation. It's tiny. It's e to the minus s, and it's somehow the photons that have been reprocessed through a black hole have some e to the minus s correlation with, the black hole from which they came. But it is a non-local interaction as opposed to a non-local entanglement of states, I think. But that's what I'm hearing anyway.
Yeah, so I would phrase it as, one needs something like a non-local transfer of entanglement. And what I was just saying with regard to at least the wormhole story in the approximation that we thought about sort of in the older work is you don't get the kind of non-local transfer of entanglement you need for this story. Now, again, maybe this whole present story somehow goes beyond that approximation and corrects it. That could be sorted out.
Stan, you have a comment then, or a question? And I see that we're bumping up against an hour, a session that was nominally scheduled to last 45 minutes. I'm happy to continue it.
I think we should
but maybe I should ask,
bit.
at this point, I should ask my bosses what they'd like to do.
Who's your boss? We moved it about 15 minutes later just to give everybody a bit of a break. So I think we can overrun by 15 minutes. So when was it supposed to finish?
It started an hour ago, right?
Yeah, I think we can go another 15 minutes if everybody's happy with that. I think there's more to be discussed.
Okay, very good. All right, Stan, you have been patiently waiting. We can't hear you.
Can you hear me?
Yes.
Okay. I'd like to go on to continue a bit, because I'm a bit confused with this seeming dichotomy between entanglement and non-locality, because I had thought that entanglement is almost by definition something non-local. So if I have entangled states, this is a non-local statement, and then so I'm a bit confused. I was wondering whether Steve could say something more about what is meant by non-local transfer of entanglement, since the entangled states are non-local. And my further question, perhaps to Juan, would be whether this proposal, the EPR proposal, wouldn't that mean that, okay, if I have a wormhole, doesn't that mean that this is a non-local term in any Hamiltonian anyway, by definition, and therefore if it describes entanglement, then all well and good. It is a way of describing a non-local effect. Fine, but then the question is whether, as Nick was saying, whether there's something more beyond wormholes that need to describe the entangled states that are supposedly counted by entangled entropy and something like that. I'm sorry if this didn't make much sense, but I tried to phrase the question a bit.
Well, yeah. So I think, yeah, indeed, you have this. Yeah, these wormholes that have to do with entanglement, right? But I think the question that was being asked was whether we have some kind of direct interaction between something which is, for example, in the black hole interior and the radiation. So the idea is that there is the black hole interior and it's connected by entanglement with the radiation. So you could think of that as that entanglement, you can view them as tiny wormholes that connected to the radiation. And the question is, how do we get the information that is in the interior? Because it does seem to be space-like separated from the radiation. And I think we don't have a simple Lorentzian picture that where you would do a unitary transformation and get this information out.
Would the wormhole that you construct realize?
Well, I mean, I think what you need to do in the Lorentzian picture is to try to you start with the radiation and you start to shrink this wormhole. So you start to make it smaller and smaller until you get to the quantum extremal surface. And this requires some large number of operations. It's a kind of Grover search, and well, it's but yeah, the way one could picture is perhaps you're just shrinking the wormhole and you extract the information in that way.
The width of the wormhole, or the length.
There is you have the black hole and the quantum extremal surface just behind the horizon, and then you have the whole warm black hole interior, right, which is entangled with the radiation, right? Let's think of that entanglement as tiny microscopic wormholes. The goal is to act with the radiation, just somehow to shrink all these wormholes and bring it all the way to the quantum extremal surface. Then you would have extracted all the information. But this is just words. I mean, I think Rafael was saying earlier that one should not maybe make overblown claims. So the real concrete calculations are, I think, the calculations of the entropy. So you can calculate these entropies, and it's a well-defined calculation from beginning to end, and the rest is a bit of interpretation and philosophy.
So I see there was a hand up and then turned into a question in the chat from Seth Corin. Do you still want to ask your question, Seth?
Sure. So I'm not primarily in this, and a young person who just knows things from reading very many papers from the last 40 years. But it seems to me like everyone, the wormhole ologists, replicaologists, would agree that the finite size of the wormhole in this new story is one of the really key new features, right? There's some sort of non-locality that, as Steve was saying, it is needed. You need more non-locality than was shown not to be enough in the 80s. And it seems like there's some, we don't fully understand it, obviously. There's something sort of new, but there's some non-Wilsonian sort of thing going that's preventing you from taking the Planck mass to infinity smoothly. And that seems to satisfy, well, is that enough, as a question, let's say, is that enough non-locality? Could that be enough non-locality? Because I know that's an imprecise statement to satisfy everyone here. Thanks.
I would repeat what I was saying before, which is I don't think we need more non-locality than that is implicit in including various geometries in the path integral.
Okay, Nick, I see you have your hand up.
Yeah, just one, I was going to take it a different direction, sort of stimulated by sort of what Raphael said. And, you know, what we're looking at here seems to be, over the history of the subject, a whole bunch of low energy effective theories with interesting Euclidean saddle points that appear to count something. And what we don't have is the UV completion. And so is this really, all this story, just yet another example of an effective Euclidean field theory with a saddle point looking for a UV completion in a Lorentzian section? And I suspect that's what we're really haggling about. I don't know if anybody wants to pick it up and run with that thought.
Yeah, I think it's conceptually similar to the Gibbons-Hawking entropy formula.
That's exactly what I had in mind. I sort of raised on this.
It's part of the data that we have, and we use it.
Well, it's a miracle. You know, I was raised on Euclidean quantum gravity, and it always struck me as an absolute miracle that there were these gems that Euclidean quantum gravity pick up, and then the rest of it was garbage. I mean, you know, uncontrolled path integrals, but yet there were the gems. And so, in some sense, what we've just discovered is another one of those gemstones. But the point is that we had no idea 40 years ago what the UV completion of Euclidean quantum gravity was. Now we've got an idea. Of course, it's string theory. And so I think one should be looking for the UV completion of this story in string theory. So that's the sort of thought I want to throw out there and just see whether people, in the interest of building bridges.
Well,
I think you're right. I don't know if I can comment on that briefly.
Sure, go ahead.
Yeah, but I think you're maybe underselling a little bit the how amazing it is that gravity knows these things and that it contains these gems in the first place. And you know, if you're in the mood for operating the way that we used to do physics, which is to sort of start from what we know and not hope that the final answer falls into our laps, then these are really valuable data points. Right? We're starting with a theory which is extremely well tested, and we're getting these results. You know, if you were a skeptic, if you'd never heard of ADS-CFT or string theory, this would have been the first result that would have suggested to you that information actually comes out of a black hole. And historically, that's not how it happened. But it's a valuable data point if you want something other than, you know, be lucky enough to know the final answer in one
to
step.
some extent, we got the first new answer on black hole information from Strominger. Actually, Sen deserves a chunk of credit for that. Sen, Strominger, and Buffer. String theory suddenly started counting states in the right way. And once you've got that data point, that's the one you kind of should run with. What do these things look like at strong coupling? This is, to some extent, how I got into the fuzzball program. It's sort of simply asking the question, the one new piece of data we got in 1996, and you just should run with that because string theory seems to be the ultraviolet completion. And so why are we going back to Euclidean quantum gravity in 2 and 3 dimensions, and yet again trying to reinvent the wheel in a framework that we know is very, very limited?
Well, it's not that limited. I think that's what we learned. That it's less limited than we thought, I think. And,
yeah, okay.
But I agree with your point that we have string theory, this very powerful theory, and we should definitely know more of what I think. Yeah, string theory is kind of bridging the weak and strong coupling, and we should probably holds many more lessons for us, probably more than just ordinary gravity. We have to probably also extract those lessons.
Yeah, I guess the sticking point for me is that the Euclidean methods there is no there's no interior to talk about. I don't know if others would agree with this or not, but it seems to me that what one is doing is one's taking the exterior, for which, you know, the effective field theory, I think most people would say the effective field theory is a perfectly good approximation to the exterior. And then one is taking that exterior effective description and analytically continuing it to the interior. And somehow that's smart enough to know very interesting detailed properties of you know, things like the page curve, the Bekenstein-Hawking entropy, and so on. But it seems to run afoul of the sorts of things that Samir was presenting, namely this tension between extending the effective field theory into the interior and taking it seriously. Seems to run into some kind of paradoxes about whether corrections are small or not, just inside the horizon. And the sort of analogy I keep coming back to is one, if the fuzzball is some sort of other phase of string theory where, you know, like n equals 4 Yang-Mills is deconfined, then is one doing something similar to taking a confined phase and analytically continuing it into the deconfined region where somehow magically it's giving you some some results, but it's not actually telling you the actual microstates that are involved in giving those results.
Well, the answers that one gets using for the page curve and so on, they depend on the geometry of the interior, at least to some extent. So,
but the geometry that you arrived at was arrived at by analytically continuing the exterior.
Well, it was just by doing the Lorentzian evolution. I mean, just doing ordinary evolution from the past, right? So it's just
right. But so I asked during your talk for clarification whether what was going on the island was more than a complete knowledge of what you sent into the black hole plus the Hawking process and the effective field theory, and you said that was sufficient. So to my mind, that's taking the exterior geometry and analytically continuing it using low energy effective field theory to the interior.
Yeah, well, I'm just saying it's just the evolution. I mean, we're just using the evolution in gravity. It's not
in effective field theory, yes.
Yeah, in effective field
but that
theory.
seems to be in tension with this small corrections theorem.
No, I don't think it is in tension with the small correction theorem. So I think that what removes the tension is this, that the tension only arises because when you think that the whole interior is described in the Hilbert space of microstates, of black hole microstates. But the idea is that the Hilbert space of black hole microstates only describes up to the quantum extremal surface. And once you have that, I think the tension disappears.
I guess I would disagree with that a little bit. I mean,
yeah. Okay. Go ahead.
This was a comment also I felt, you know, when AMPS wrote their paper, they didn't make the assumption that the Hilbert spaces are distinct. You know, we'd all grown up on the idea of black hole complementarity and the idea that the Hilbert space of the interior is really just another version of the exterior. The point was to show that you still have a problem at the horizon, even if you accept that assumption. Of course, there are more sophisticated ways that you and others developed of trying to get around this issue, but it's not as simple as saying, oh, I just have to remember that the Hilbert spaces aren't independent. I think that the tension with the AMS or Mathur type arguments goes away if we accept that the calculation that we're doing using the Euclidean, or really a general gravity path integral, simply shouldn't be expected to give us answers to all the complicated questions. It's amazing that it gives us answers to some relatively simple questions. But if it doesn't tell us what the outstate is, and in this calculation, the outstate is manifestly that of Hawking, so it's clearly wrong according to most of our expectations, then there's also no reason to expect that the horizon is smooth because it's one and the same step that gives you that, that result. Maybe it is smooth for some other reason, but it's not smooth because that step appears in that calculation.
Somebody who has their hand up. Vishnu.
Yeah, Vishnu, you want to ask a question?
Yeah, so I just wanted to make a small comment. It's basically based on the discussion that you guys were having on the wormholes and this modified inner products in the PSSY paper. So, so there's a non-provocative way of looking at these calculations. So it seems that an equilibrium approximation or a local equilibrium approximation can help you derive these modified inner product relations. And this has been done in Hong, Liu, Varthan, and also another paper that I wrote with Chad and Krishnan. So so the basic idea is that so you have some sort of an equilibrium approximation, and it replaces, and it gets replaced by an ergodic stand-in, and in this and their ensembles play a role, and in fact you can derive these modified relations, and it has precisely the same structure that's there in this PSSY paper. So the reason why I like this method is because so there's no non-locality here, and the ensemble averages and all these quantities arise the same way ensembles emerge in a statistical mechanics or a general non-gravitating thermodynamical system. So I think that it's relevant to the discussion that you guys were having, because you can actually replace all these non-locality arguments with just a simple equilibrium approximation, and I feel that it's nicer in some sense. So I thought I just mentioned that.
Any of the panelists like to comment? If not, we can move on to Nayesh. I believe you next had your hand up.
And then after that, I think we should wrap up if possible, because it's getting a bit late and our panelists are probably getting tired.
Okay, last question.
I was just going to make I guess maybe a question / comment that, I mean, I think these seems that two very fantastic stories, but if you don't actually have observable predictions, they remain as stories. And as far as physics is concerned, they don't really help. So, I mean, maybe you can argue otherwise, but I think, I mean, at the end of the day, if your stories don't lead to predictions, then that can be observed this in the next 100 years or so. Then I don't think that really helps to advance the cause of physics. So, I mean, do these stories lead to distinct predictions?
The calculation of the page curve leads to a prediction in the sense of what entropy to expect from an evaporating black hole, but it's a prediction that is hard to check for an astrophysical black hole or for a black hole that you could imagine. And it would be very difficult to make a black hole for which this prediction can be tested. Maybe it could be tested for a black hole you can make in the lab by some analog system. So some of these ideas are related to quantum teleportation. They're a form of quantum teleportation, and maybe you could do some experiments inspired by some of these ideas that could check some of this for toy gravity models. I think if you ask me, I think it's more likely that we'll get to prediction by understanding better black holes and understanding perhaps the best bet might be that by understanding better black holes, we'll understand some new effect in cosmology, and maybe that could be observed. This has already happened with black hole physics. So, for example, the Hawking effect is not measurable for astrophysical black holes, but there is a very similar effect, which is the creation of primordial fluctuations that can be measured in cosmology.
Okay, and on that note, I think it's probably time to wrap up and thank our three panelists, Douglas, who's had to leave us, and Samir and Juan, for a very engaging and provocative discussion.
I'd like to just thank everybody and all the Juan and Samir. Thank you for that amazing afternoon. There's a homework assignment, perhaps for Douglas and Samir. In the chat, there's been a proposal that Douglas and Samir have a discussion on the details of islands and end of the world brains, and some later date recorded for posterity, give some presentation to that effect. Samir, please would you approach Douglas and we'll try and set something up. But I think that would be great. But anyway, in the meantime, thank you very much to everybody. It's been a